Hello, Precalc. So we are starting our next unit, Unit 6, and it is all about rational functions. So you got this packet yesterday and asked you to complete most of it. We're going to go over a couple of the answers right now, the ones I think that might have been a little bit tougher, and we're going to fill in the ones I told you not to fill in. All right, so number one, if you have 1 over x, what are the possible values of x and what are not possible values of x? So I hope you got that x cannot be 0 because we cannot divide by 0. And remember, when you're thinking about fractions, think of it like division sometimes when you have to think about what's possible, what's not possible. Is it possible to like take a piece of paper and divide it into 0 pieces so that you have 0 pieces at the end? And that's not possible, like unless you like light the paper on fire. So we cannot divide by 0, and anything divided by 0 is actually undefined. So right here, this is really important. Undefined, dividing by 0. All right, the next question I want to go over is number 2 of the starter. What is a rational number? Like, give a definition and give 3 examples. So some of you put things like, rational number is a number that can be turned into a fraction. It's a decimal that has a repeating pattern, things like that. And these are both true, but I'm going to give you the official definition of a rational number. So I would like you to have this in your packets, so please write it down. A rational number is any number that can be expressed as, or that can be written as, P over Q, where P and Q are integers. And since this is a fraction, we know that and Q cannot equal 0. We cannot have zeros as the denominator. And so some examples of rational numbers, 2/3, -9/6, 2.3333, because this can be turned into a fraction that follows our definition. Some things that are not rational numbers, or not rational numbers as they're written. They can possibly be transformed. So some non-examples. 6.4 over 9, because 6.4 is not an integer like we said these have to be. 12 over -57.1, not rational. 3.1246982 ... There's no pattern to this repetition. Like, we know this decimal will go on forever, but unlike 333 or even something like 0.565656, you know what, let me write that in black so we know it goes with the examples. There's still a pattern to this one, but there's no pattern to this one, so no pattern here. So not rational. So it cannot be turned into this fractional form. All right. So now that we know what a rational number is, we can actually have the definition for a rational function. It's a very similar definition. So a rational function, it is a function. Let me write that better. A function of the form f of x equals p of x over q of x. So before we had p over q where they were integers, now we have p of x over q of x, where p of x and q of x are polynomials, and q of x does not equal 0. So the parent of rational functions, that means the most basic rational functions, is the one you worked with yesterday. The parent function is 1 over x. So there's our definition for rational functions. All right, after this, you have to fill in your table. I trust that you were able to fill in your table, whether you used a calculator to help you or whatever. So I'm going to be posting this online. So you can pause the video here if you want to check your table, but you can see that, on table 1, as x got bigger, then our f of x got really, really small. And when x is a very small number, f of x becomes very big. So it's just like looking up and down. X is very small is at the top, small x, bigger number, bigger x, smaller number. And then on this last page, you were asked a graph. Your graph should look something like this. This is called a hyperbola. That's what 1 over x is. So here's a hyperbola, the hyperbola graph of 1 over x. And I asked you to fill in most of this table, but we're going to go over most of these. So we know for the domain, there is one value that x cannot be. So that value is 0. And I'm going to write all of these in, I'm going to go with interval notation because that's mostly what you're working with next year in calculus. So let's get more used to it now. So we can't write like negative infinity to infinity because there's a value that we can't use. We have to split this up at 0. So we have negative infinity to 0, don't include the 0, use parentheses, combined with 0 to infinity. Now, if you used inequality notation or step builder notation, that's fine too. But I'm going to be using interval notation. All right, now our range, if we look at our graph, it looks like there's a y value that cannot happen as well, and that's also at 0. So our range is actually going to be the same thing as our domain. So negative infinity to 0 with 0 to infinity. And because of these, we can see since they're never going to reach these x equals 0 and these y equals 0, these can be considered our asymptotes. So we can figure out these other two boxes down here. Our vertical asymptote is when x is equal to 0, otherwise known as the y-axis. The horizontal asymptote is when y equals 0, otherwise known as the x-axis. All right, now because these two are asymptotes, we can consider them basically as like non-touchable values. So there's not going to be an x or y intercept. We do not cross these lines, so can't have these. And the last box I asked you to fill in was where is the function increasing and decreasing. So if you remember from Algebra 2, you read a function from left to right, and you have to decide, oh, is this function going up? If it's going up, then it's increasing. Or is it going down? Then it's decreasing. So I'm going to follow along the function from left to right. So here, the function is going down, which means it's decreasing. Okay, I'm going to follow along the rest of the function from left to right. Still going down. So this function is always decreasing. It never increases. Always decreasing. So I'm going to write never increasing. And if you want to write where it's decreasing, it actually is going to be the same as the domain. So decreasing on negative infinity to 0, and then from 0 to infinity. Technically, we don't include the 0 because nothing happens at 0. The function, there's no action on the function 0, so it can't really be decreasing. All right, end behavior might be the one thing that you might not be so sure about. So let's go over it. End behavior. That's what happens when x is approaching infinity and x is approaching negative infinity. So let's take a look at the graph. As x approaches infinity, that's actually kind of what we just did. So we're following the function as x gets bigger and bigger and bigger. So we're reading left to right. So we read, let's see, we read here, but we can get closer to infinity, we can go here. So as we get closer and closer to infinity, what is happening to our function? What happens is our function is getting closer and closer to 0. Like you can see that it stays very close to the x-axis, whoops, but it's never going to reach it, but it's getting closer and closer. So as x approaches infinity, f of x approaches 0. And now let's see what happens as x approaches negative infinity. So instead of reading from left to right, if we want to approach negative infinity, we have to go right to left. So starts here, go into the left, but we can get closer to negative infinity. So starting here, going further to the left, 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 left. And we know there's an asymptote. So we're going to keep on getting closer and closer to the x-axis, but never touch it. But again, the same thing kind of happened. The function is approaching the x-axis, which means the function is approaching 0. These are concepts that will be very important for the next unit and behavior. All right, and then the last question was whether the graph is symmetric about the origin. There is the answer. So pause the video if you need that. But after you copy these notes down, I have a question for you, an extra question for you to answer to see if you understood. So please make sure to answer that question. And that's your work for today. All right, guys, I missed you. Stay safe.